Let me thank Urvashi and her team for organizing this conference. It's been great. Nice discussions, new friends, new ideas. So what can you ask for more? So I'm Lorenzo Maccone. This is joint work done with Arun Pati, who's here, and Hubert de Vries, Barry Sanders, who will be here next week, I understand, and Namrata Shukla. And I'm not going to talk about dinosaurs, but there's a trick with the dinosaur pictures that you will remember the pictures and you will remember my talk. So I'm giving away the trick behind my dinosaurs. See, they look like uncertainty relation products. So this is like a Gaussian, you see? OK, whatever. So what am I going to talk about? I'm going to talk about uncertainty relations. And if you think about it, the Heisenberg uncertainty relations with which you're all familiar with do not really convey truly the notion of complementarity between observables. Why is that? Because the product between standard deviations can be 0 if A and B, even if A and B are incompatible. Because, for example, if you calculate the state, these products on an eigenstate of one of the two, both of these terms are 0. And you get 0 greater or equal than 0, which is really not very informative, OK? So, for example, if you take the state of the system, an eigenstate of A, then this product is 0. The expectation value of the commutator is 0. I mean, this is really not very useful. So can we do better? This is our question. And the answer is yes, because we can we can do better. And before showing you how you can do better, let's remind you that the Heisenberg uncertainty actually is called Heisenberg, but it was derived by Robertson. This equation here is calculated on the system state A. And of course, you can do a little better by, and this was done by Schrodinger almost immediately, by taking another term which involves the anti-commutator. They usually have the commutator, the expectation value of the commutator. You can take the expectation value of the anti-commutator. That's the Schrodinger uncertainty relation. But all of them become trivial if psi is an eigenstate of A and B, as I was saying. So how can we do better? Well, can we give a lower bound to the sum, OK, of the variances? So the sum is 0 only if and only if both of these terms are 0, OK? Whereas the product can be 0 if only one of them is, OK? So a simple try would be, OK, we have that the difference to the square is always greater than 0. And this implies trivially that sum of the variances is bigger than the product. And we know that the product is bigger than the Heisenberg. So this could be a first very simple try, but it doesn't really work, because it's true that this is non-zero only. This is 0 only if both of them are 0, but then the lower bound is 0 again if the eigenstate is, if you're calculating it on an eigenstate of A and B. Okay, so we want something that has a non-trivial lower bound. So before showing you how to do that, let me go back and give you a visual interpretation of the Heisenberg uncertainty relation, which is useful. So if you look at the product, I mean, if you plot if you take the random variable A on one axis, the random variable B on another axis, then clearly the product of the standard deviations is just the area of these uncertainties, OK? So you plot the uncertainty of B here, the uncertainty of A here, and then the product is just the area of this box. But if you take the sum, OK, this is the square length of the diagonal, OK? So it's analogous, but you see immediately that the area can be 0 if one of the two sides of the box is 0. But the diagonal will not be 0 unless the whole box shrinks to a point. So this is the whole idea we are exploring. And of course, you can extend this to multiple dimensions, to more than 2 observables. Like in this case, The product is just the volume of the box that contains the uncertainties, while the sum is just the square length of the diagonal. Okay? So this is the main idea we're going to explore. Of course, since we are taking the sum instead of the product, we need a dimensional regularization if the A and B have different units. So you just need to divide by something which takes away the unit so that the sum makes sense. Okay, this is just a trivial statement, but it's important to remember. So what are the main results we managed to derive regarding the sum of the sum of the variances? Well, we have some state-independent bounds. If the observables form an algebra, okay, these are, I'm going to go through these in more detail, but we have results for some algebras, and the lower bounds are state-independent, and we have state-dependent bounds for arbitrary observables, and this is, you take an arbitrary A and an arbitrary B, we can find an L, which is a lower bound, but it will depend on the state. So this L will be a function of the state, whereas in these cases, you see that these lower bounds are all functions of the algebra, Casimir's, and they are state independent. They are constants, okay? They just depend on the properties of the algebra. So let's start from the case of the algebras, and let's look at how it works. Let's start from just a very simple case, the Weil-Heisenberg algebra, X commutator with P is equal to I, and we have an uncertainty relation of this type. This is quite trivial, actually, but that's what it comes out for the Weil-Heisenberg algebra. A much less trivial algebra is the SU11 case, okay? The algebra is defined by these commutator relations. And it turns out that you can give an uncertainty relation for the sum of the variances of this type. Of course, here you can put a plus sign. And of course, if you put a plus sign, this is bigger than what I put here. So we can even get a tighter one if we put a minus. And K is just the Casimir of this algebra. And then analogous, we can give an uncertainty relation for the SU2 case. Okay, the algebra is defined in this way. And the sum of the variances is always greater than J. And the SU3 case, and you get a lower bound, which depends on the irreducible representation labels, and so it's a constant. And similarly for SU4, SU5, I didn't put it here. You can find the expression on the paper. It's a little bit more complicated, not much more complicated than this, but it's similar to the SU3 case. Of course, the Weil-Heisenberg case and the SU2 cases were already known. The SU2 case was, well, the Weil-Heisenberg case is trivial. You can derive it very easily. And the SU2 case was rediscovered many, many times. But what we did was to put all these cases in a unified framework, okay? So to show how all of them can be derived in a single way. And just to give you an example how it's derived, I mean, I don't want to go through all the calculations, but just to give you a flavor of the calculation, let's derive the case of the Weil-Heisenberg. Okay, so this is the uncertainty relation we want to derive. First thing is to take the square of the operators of the algebra and connect them to the Casimir. Okay, the Casimir, it's not really the Casimir in this case, but you can think of the identity as being the Casimir of the Weil-Heisenberg group algebra. And then you have this extra term, which is connected to the A dagger A, which are defined in the usual way. Okay, so connect the square of the operator to the Casimir, and then look at the average of the squares, and just use a simple application of the Cauchy-Schwarz inequality, the easiest thing you can think of. Just gives you a term which takes away this. So when you go and calculate the sum of the variances, you have the expectation value of the square minus the square of the expectation value. Sorry, there's a typo here, of course. this term cancels this, and you're left with a Casimir. Okay, so this is what happens for the Weil-Heisenberg case. Of course, you can derive this much more easily than this, but in the other cases, no. For the other algebras, that's the easiest way to derive this. So the procedure is connect the Casimir with the sum of the squares, bound the averages with a Cauchy-Schwarz inequality, and then you're only left with the Casimir. Okay, this is the thing that really works for all the cases we have analyzed, and of course we think that it will work also for more general cases. We haven't gone through all of them yet. So what about genetic observables? So if you don't have an algebra structure to help you, these Casimir constants, what happens? Well, we know it's going to be complicated to obtain a state-independent bound for genetic observables. Unfortunately, it's not going to be as easy as getting a lower bound for the Heisenberg Robertson case, which is state-dependent, by the way. And we know that because we have some results on this. For example, this paper by the Werner group, they give a constructive but numerical procedure to obtain such lower bounds. It's very complicated. And also, Arun was giving here a talk on Monday, I think, about these kinds of things. And also, his procedure is rather complicated. So we know there won't be, at least, we don't know, but we don't think there will be a very simple one. It would be nice to have a simple expression for the sum of algebras like Robertson one, but doesn't seem to be possible. But it is possible to give state-dependent lower bounds, and this is work that I did with Arun Pati, and we gave two state-dependent lower bounds. Okay, so we have the sum of the variances, and we have a lower bound, which is non-zero, except, of course, the case in which the psi, the state of the system on which you're calculating the variance, is the joint eigenstate of A and B. Okay, in that case, of course, it must be zero. And we have two different such bounds, one with L, one with M, and of course, this means that the sum of the variances is greater than the maximum of these two quantities. Okay? Let's start with the first, L, the first bound. Well, the sum of the variances is greater or equal than this term here. This is our expression for L, where, of course, we choose the sign, this plus or minus, we choose it so that this expectation value of the commutator is positive. Of course, it's real if you multiply by I, and then you choose this sign in such a way that this is positive. Okay, and then this psi perpendicular is just an arbitrary state which is orthogonal to the system state psi. Okay? And in our paper, we give a constructive procedure to choose psi orthogonal, or just choose any random one you want. And if you choose a random one, almost for sure this red part is going to be non-zero. Okay, and oops, sorry. Yeah. The green part here is what comes out from the Heisenberg-Robertson uncertainty relation, while the red part is a new part, which, of course, is, as I was saying, almost always different from zero, except if psi perpendicular is a joint eigenstate of A and B. Okay? So, of course, we can think of minimizing over psi perpendicular. This means that this red part is zero. If we minimize over psi perpendicular, we can always put this to zero. And so we're left with a Heisenberg-Robertson one, the green part. Or we can maximize over psi perpendicular, and then we show that this inequality, if we maximize over all possible psi perpendicular, this inequality becomes an equality. So this is a tight bound. And these are some examples with randomly chosen states for psi perpendicular for the case of the sum of two components of the spin. Now, okay, the proof, I'm not going to go through the proof, but just to say that it's just an application of the Schwarz inequality. So it's very simple derivation. And actually, we must credit our referee, which turns out is Masanao Ozawa, for this proof, because the proof in the first version of the paper was much more complicated. But the referee say, oh, but you can prove it much more easily. And that was a really nice referee report to get for once. And we must thank Masanao for that. And okay, and here I just give you an example for the harmonic oscillator. And it turns out that you can choose, and you can have Fock states. And Fock states are minimum uncertainty states for this relation. And also coherent states are minimum uncertainty states for this relation. And of course, for the Heisenberg-Robertson case, the minimum uncertainty states are coherent states, while in our case, also Fock states are minimum uncertainty states. Okay, of course, these are just examples. In reality, the class of minimum uncertainty states is much larger. It basically covers the whole Hilbert space if you optimize. So, what about the second bound? The second bound is obtained by saying that the sum of the variances is always greater or equal than 1/2 the variance of the sum. Okay, and this is very simple, and it's the nice thing is that it's very simple. The not so nice thing is that it can be 0 if you calculate if the state of the system is an eigenstate of the sum of the observables. Okay. Also here we calculate for some random cases, and the proof is very simple. It's just a simple application of the parallelogram inequality, and you can obtain that inequality immediately. So both our bounds are state dependent, like I was saying, and they depend on the state. Can we use them to get a state independent bound? And this can be done, of course, if you try to optimize over all possible states, but not for the second one, because it becomes trivial. It's 0 when it's an eigenstate of the sum of the observables. The lower bound becomes 0, so you cannot use the second one, but you can use the first one. So you minimize over psi, the state, and you maximize over psi perpendicular, and you get a state independent bound. But of course, that's not a very nice closed expression. But still, you can give a state independent lower bound from this. And using the same technique, it also turns out that you can get a tighter version of the Heisenberg Robertson bound. So this is the Heisenberg Robertson bound. I didn't take the absolute value of the expectation value of the commutator, but I just multiplied it by I and put the plus and minus. But this is exactly the Heisenberg Robertson bound, the usual uncertainty relation. And it turns out that using the techniques we had, we can just divide this bound by this expression here. Again, you see that this psi orthogonal state comes out, and this gives a tighter bound. It's still true, but now typically this expression is bigger than this expression. Okay, so you get a tighter bound. Now, one thing which is very important when we talk about Heisenberg uncertainty relations, there's a very common misunderstanding about this, which maybe is forgivable because it's a misunderstanding that comes from Heisenberg himself. And there's a misunderstanding between preparation versus measurement uncertainty relations. These two notions are very, very different, okay? I want to emphasize this a lot. And this confusion originates because there is this confusion already, as I was saying in Heisenberg's paper. If you take Heisenberg's original paper and you look at the end, you see that Heisenberg writes that his paper has been criticized by Bohr, also because of this reason. So already before publication, Bohr was already criticizing this paper, and so there have been a lot of criticism about this. So what is the difference between these two notions of uncertainty? So measurement uncertainty relation refers to the measurement disturbance trade-off. So if you perform a precise measurement on a quantity, you will induce some disturbance on a different quantity, on an incompatible quantity. Okay, and this is very difficult to define rigorously what disturbance is. So there's a very strong debate in the literature, especially recently, about how you can really quantify this disturbance. Okay, and for example, Masanao Zawa has one proposal, and of course there was a very strong debate about that. Well, if you talk about uncertainty relations, the Heisenberg-Robertson relation, this is the wrong interpretation to give to it. Okay, so this is not good for the Heisenberg-Robertson uncertainty relation. And this was pointed out, for example, by Ozawa. He gives a different uncertainty relation that is good for the measurement case. Okay, but if you want to capture the notion of measurement disturbance relation, you should not use the Heisenberg-Robertson one. Okay, what is the correct one? The correct interpretation refers to the preparation. So you're talking about preparation uncertainty, which refers only to the preparation of the state. You can't prepare a state which has sharp values for incompatible observables. Okay, it only refers to preparation and not to the disturbance. And in my talk, I'm only talking about preparation uncertainties. Okay, so all the relations I've talked about refer to the preparation and not to the disturbance. I really would like to to explain it by using Asher Perry's words. This is taken from his book, and probably also from some of his papers, because in his book he put many of his papers. So the only correct interpretation of the uncertainty relation for X and P is the following. If the same preparation procedure is repeated many times and is followed either by a measurement of X or by a measurement of P, the various results obtained for X and P have standard deviation, delta X and delta P, whose product cannot be less than h bar over 2. There never is any question here that a measurement of X disturbs the value of P and vice versa, as sometimes claimed. These measurements are indeed incompatible, but they are performed on different particles, all of which were identically prepared. Okay, so it's only that they are in the same preparation procedure, but the measurements are done on different particles. And therefore, these measurements cannot disturb each other in any way. The uncertainty relation only reflects the intrinsic randomness of the outcomes of quantum tests. Okay, he's talking about preparation uncertainty. Okay, he doesn't want to talk about measurement uncertainty. He calls that uncertainty principle. He doesn't want to talk about that, but still you can find the word uncertainty principle in his book. You can look it up in the index of this book, and you will find that the only place in the book where uncertainty principle appears is in the index, and it refers to itself. So that's funny. You can look it up in his book. So just to conclude, what did I say? I talked about stronger preparation uncertainty relations with non-trivial lower bounds. These are preparations which are defined for the sum of variances, because you cannot do that for product of variances. You cannot have state-independent ones. And I've shown you how to get state-independent ones for algebras. And this is joint work with Barry Sanders, Namrata Shukla, and Hubert de Guise. You can find in this paper. And then I've shown you how you can get state dependence for arbitrary operators for the sum of variances, and this is joint work that you can that I did with Arun Pati. You can find in this paper. Thank you for your attention.
Independent variance-based uncertainty relations that you were talking about. So far as I know, there has been one proposal by Huang to construct variance-based uncertainty relations that are state independent. So have you checked your state independent uncertainty relations with the Huang's results to see which one is tighter?
Which one?
Huang in 2010 PRA.
No, I don't know.
So have you
this.
checked whether that is tighter or this?
Sorry, I don't know about this.
Thank you very much for such a nice talk. I just want to ask, like, for these algebra uncertainty relation, are they tight?
Yes, they are tight.
And what are the minimum uncertainty states in each case?
They are typically they are the coherent state of the algebra, as you would expect.
Okay, thanks.
Yes.
Regarding Heisenberg uncertainty relation, you mentioned that work by Ozawa, but there is another direction work by Paul Bush and his group, that the measurement uncertainty relation considering joint measurability. So what is your comment about that?
Joint measurability, you mean?
Joint measurability of incompatible observables.
Yes, that is going to be, that is going to fall under the other type of uncertainty relation. It will be a measurement type uncertainty relation. So I don't know how this would connect to that. I haven't thought about measurement uncertainty relations, to be honest. Okay.
Is there any extension to the entropic case of yours?
Oh, yeah, that's a good question, because indeed the entropic uncertainty relations were introduced exactly for this reason, because people wanted to have uncertainty relations with lower boundaries which are state independent. So this was one of the motivations of David Deutsch when he introduced the uncertainty relations, the entropic ones. So yeah, we are trying to do the analogous thing, but for variances, because variances capture somewhat different notion of incompatibility, of uncertainty. The entropy only looks at the eigenstates, in a sense, of the observables. It doesn't depend on the eigenvalues at all, while the variances do. So they are capturing different notions of uncertainty, I would say. So of course, the entropic uncertainty relations, there have been a lot of work on this, and also there are some very nice ones. But we wanted to do the same for variance. So that's the idea, the whole motivation for this.
Thank you.
Thank you.
You mentioned that the sum uncertainty relation, the minimum uncertainty product for Fock states.
Yes.
Whereas for the product type, it's for the coherent states. So is there, so what does it physically implication of that result? Means minimum uncertainty product. Can you expand a bit on that?
Yeah, I mean, maybe that's a little confusing, because when I say minimum uncertainty, I mean that inequality, the uncertainty inequality is satisfied with an equality. But in reality, any state, if you optimize over the psi perpendicular, is satisfied with equality. Huh. So this maybe was a little confusing, because then any state is basically a minimum uncertainty.
Yes.
So,
that is what.
Yeah. So I wouldn't know the physical meaning of that, but
So in that
you
sense,
shouldn't think about Fock states in particular.
brilliant.
Right.
Okay, okay. So that was, I was a bit confused.
Yes, yes. I apologize. That's
No,
my fault.
thanks,
Yes.
thanks.
Do these sum uncertainty relations, do they have nice covariance properties in the sense that, for example, in the context of Heisenberg, while Heisenberg Robertson Schrodinger uncertainty principle, you have the property that under linear canonical transformations, the form of the uncertainty relation is preserved. Is there any nice covariance property one can discover in these relations?
That's a good question. I don't know.
Huh?
No.
Because that will be interesting
Yeah,
because
sure. I
that
agree.
particular covariance property has played
Sure.
an important
Well,
role
it's-
in.
It's probable. Yeah, I would say it's a good guess, but I don't know. I never thought about that.
Thank you.
Yes.
So my question is the following. One of the strengths of the delta x, delta p principal uncertainty, whatever you want, relation, whatever you want to call it, greater than h bar by 2, is that the observables on the left don't make any reference to Planck's constant. And so as a result, that's what gives that relation, I think, its strength, that those observables are defined a priori, they have a meaning classically. Whereas your relation, if you write it in terms of x and p, the one for x and p, you have to de-dimensionalize x and p by using some reference
Sure,
oscillator
sure.
or something.
Sure.
So that's sort of another, does that, so I wonder what that does, and maybe another way of asking that is if you then tried to optimize or strengthen your uncertainty relation by variation with respect to the frequency of the reference oscillator, does that?
But if you're looking at oscillators and you take h bar equals 1, then you can sum them. X and p have the same.
No, but h bar is
the same
but we-
dimensions.
That's a
Is that what
curious
you're asking?
sort of thing. There is still the notion of a reference oscillator in there.
Yeah, but if you, all I'm doing is writing x and p in terms of a and a dagger,
But that
x and p in this.
yeah. So what I'm saying is,
H bar is equal to 1 when you do that, right?
if you
That's
now
what
try
I'm
and
doing.
minimize or maximize with respect to omega reference, do you get a trivial result or is it still meaningful?
No, I think you still take the same result. I mean, this is always true, so
Okay, all right. Let's move on. Thank the speaker.
thank you.